In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer Part 81. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with formic acid is stronger than acetic acid. Chemical reasoning. Formic acid is identified as a low molecular weight organic acid and is considerably more detrimental to the paper insulation unit in transformers compared to acetic and levulinic acids. Formic acid, HCOOH, exhibits stronger acidity compared to acetic acid, that is CH3COOH, and most other aliphatic carboxylic acids, including levulinic acid. See the structural diagrams, formic acid and acetic acid. In acetic acid, where the methyl group acts as an electron donating alkyl substituent group. Formic acid and acetic acid are both carboxylic acids, but their acid strengths differ due to the differences in their molecular structures. Formic acid is configured with a carboxyl group, that is COOH, attached to a hydrogen atom, whereas acetic acid CH3COOH is composed of a methyl group, that is CH3, attached to a carboxyl group. Formic acid is a weak monoprotic acid as because the acid is capable of donating only one proton, H plus, per molecule during dissociation in an aqueous solution. Because it is a weak acid, it does not ionize completely in aqueous solution, rather partially dissociates in water to release protons H plus, forming its conjugate base, the formate ion HCOO, along with hydronium ions, that is H3O plus. The chemical reaction as follows: HCOOH plus H2O equals to H3O plus plus HCOO negative. Acetic acid is also being characterized as weak acid because in aqueous solution, it only partially dissociates in water to form its conjugate base, the acetate ion, along with hydronium ions. The chemical reaction as follows: CH3COOH plus H2O equals to H3O plus CH3COO. In aqueous solution, it is to exhibit that both formic acid and acetic acid, as classified as weak acids, so they have to undergo partial dissociation by donating proton, that is H plus, to water, forming hydronium ions H3O and their respective conjugate base formate ion and acetate ion. In both cases, a dynamic equilibrium is established between the undissociated acid molecules and their corresponding ionized form, resulting in the formation of hydronium ions, that is H3O, and carboxylate ions in aqueous solution. However, Formic acid dissociates to a greater extent than acetic acid because the methyl group CH3 in acetic acid exerts a weak electron donating inductive effect that causes to enhance the electron density on the carboxylate group after deprotonation, slightly destabilizing the acetate ion compared to the formate ion and thereby reducing the acidity of acetic acid. In case of formic acid, the carboxyl group is attached to a hydrogen atom which has a negligible inductive effect compared to an alkyl group like methyl group CH3 in acetic acid. Because hydrogen does not donate electron density to the carboxylate group, the formate ion HCOO is not destabilized by additional electron density. As a result, the acid-base equilibrium of formic acid lies further toward ionization. Through induction effect, the methyl group CH3 in acetic acid pushes electron density toward the carboxyl group COOH, which increases the electron density on oxygen atom of the OH bond. The increased electron density on the oxygen atom reduces the polarity of the OH bond compared to the more polar OH bond in formic acid, where only a hydrogen atom is present. Because the OH bond is less polar as due to the presence of nearby electron donating methyl group, mainly in the acetic acid, so the hydrogen carries a smaller partial positive charge. Consequently, the proton H plus is less attractive to a base, making it harder to remove and therefore resulting in a weaker acid. As a result, acetic acid is a weaker acid and whose pKa value is 4.76 than formic acid, pKa value 3.75 approximately, which lacks the electron donating methyl group. Presence of low molecular weight carboxylic acids and their impact on power transformers. Formic, acetic, and oxalic acids are among the most distinctive low molecular weight carboxylic acids commonly detected in aged transformer oil paper insulation systems. These organic acids are the degradation of products typically formed in transformer insulating oil and cellulose paper as a result of thermal, electrical, and oxidative aging processes. Among the three acids, formic acid is the strongest carboxylic acids and its formation is primarily the result of advanced oxidation of mineral oil, often catalyzed by elevated temperatures, oxygen ingress, moisture, and the presence of copper as a catalytic surface. Fundamental reasons for which formic acid is considered to be much more damaging and corrosive than other organic acids. This is primarily due to its higher acid strength, extreme hydrophilicity, structural simplicity, allowing rapid penetration both in oil and paper insulation, and ability to act as a powerful analyst for catalyst rather, powerful catalyst for cellulose degradation. Let's see the chart. Low molecular weight acids typically formed during oil oxidative reactions, which include low molecular weight acids, formic acid, acetic acid, propionic acid, and butyric acid. Now, the strength pKa value of formic acid 3.75 is the strongest at 25 degrees centigrade. That is, lower value means the stronger acid. Acetic acid pKa value 4.76 at 25 degrees centigrade. Propionic acid pKa equals to 4.87 at 25 degrees centigrade, and butyric acid 4.82 at 25 degrees centigrade. Acidic strength order can therefore be written as formic acid is greater than acetic acid, is greater than butyric acid, and greater than propionic acid. The tendency for an acid, particularly a carboxylic acid, to dissociate into hydrogen atoms, that is H or H3O, and carboxylate anions, is quantified by its acid dissociation constant, Ka. The strength of an acid is related to the proportion of its molecules that have dissociated into cations and anions in a solvent, typically water. And so the acid dissociation constant, Ka, is a quantitative indicator of its strength measured at 25 degrees centigrade. Higher value of Ka indicates stronger acids that dissociate more extensively, while lower values indicate weaker acids that only partially dissociate. The strength of an acid is directly related to its Ka, which is often expressed in logarithmic form as pKa, where pKa equals to minus log Ka. Therefore, lower pKa values corresponds to higher Ka values, which thus to indicate stronger acids. Low molecular weight acids, an acid dissociation constant, Ka, higher value means a stronger acid. Formic acid Ka about 1.77 into 10 to the power minus 4 at 25 degrees centigrade. Acetic acid 1.75 into 10 to the power minus 5 at 25 degrees centigrade. Propionic acid Ka value 1.3 into 10 to the power minus 5 at 25 degrees centigrade. Butyric acid Ka value is 1.5 into 10 to the power minus 5 at 25 degrees centigrade. Therefore, acid strength corresponds to acid dissociation constant. Formic acid is greater than acetic acid. Butyric acid is greater than propionic acid. Formic acid is considered one of the most aggressive detrimental contaminants in transformer oil because it acts as a strong low molecular weight catalyst for the rapid degradation of cellulose insulation, leading to significantly higher polarization and ionization losses compared to other low molecular weight organic acids. Key factors in support of the aggressive structure of formic acid. Low molecular weight acid is low molecular weight formic acid is composed of small molecular structure consisting of a single carbon atom. It has a molar mass of approximately 46.03 gram per mole. It is indeed recognized as highly soluble in transformer oil. So, it is characterized by high mobility, strong interfacial migration towards insulation paper, that is cellulose, on the cellulose part. It is a relatively strong acidic behavior that allows it to accelerate chemical reactions within the transformer because it's readily absorbed by the said insulating paper and can effectively penetrate both the amorphous or crystalline regions of cellulose. It causes severe structural degradation of the insulation material. It is considered more injurious to the cellulose-based solid insulation system that other carbonic acids because it acts as a highly aggressive catalyst for acid hydrolysis, causing twofold degradation. One, rapid reduction in the degree of polymerization of cellulose. Number two, formation of additional water molecules and acidic byproducts. And last one, formic acid is a highly polar molecule whose presence in transformer oil leads to increase the number of polar spaces in the overall insulation system. Under an alternating electric field, these polar molecules continuously realign, causing dielectric polarization losses. Formic acid partially dissociates into ions in the presence of moisture. Higher ionic concentration allows leakage current to flow through the insulation, causing to produce conduction. This conduction loss rather. Formic acid is roughly 10 times stronger than acetic acid. Because of several chemical and electrical characteristics, formic acid causes higher electrical losses in transformer oil than most of the other low molecular weight organic acids. Stronger acidity has made the formic acid to act as a dominant agent in the early stage degradation of insulating paper, causing a sharp drop in mechanical strength. Transformer insulation paper is primarily composed of cellulose, that is kraft paper, which contains numerous hydroxyl groups capable of forming hydrogen bonds with organic acids such as formic acid. These characteristics enables formic acid to interact strongly with cellulose fibers, leading to its adsorption or absorption into the paper matrix. In oil paper insulation system, in oil paper insulation system, an equilibrium distribution of substances, primarily moisture and to a lesser extent aging byproducts, can exist between the cellulose paper and the insulating oil. This distribution of substances between the oil and paper is referred to as the partition coefficient. However, moisture is the most critical component in this system as its partition coefficient significantly influences insulation health and dielectric strength. Moreover, the moisture equilibrium shifts with variations in temperature. Since formic acid is highly soluble in water and moderately soluble in mineral oil, it can readily migrate between the oil and paper insulation, often accumulating at the oil paper interface. Formic acid produced during the degradation of paper insulation in power transformers can accumulate at the interface between transformer oil and water. As a polar contaminant, formic acid has a strong affinity for water and therefore tends to concentrate in regions where moisture is present. Water molecules preferentially reside in the cellulose insulation, allowing acid molecules to be readily absorbed into the cellulose paper, that is kraft paper. And the concentration of formic acid in the cellulose becomes significantly higher than that in the surrounding oil. The acid molecules act as catalysts, accelerating the hydrolysis of cellulose chains by cleaving the glycosidic bonds. By cleaving the glycosidic bonds and causing a rapid decrease in the degree of polymerization of the insulating paper. Hydrolysis is a chemical reaction that primarily initiates breakdown of cellulose paper insulation in power transformers caused by water reacting with cellulose polymer chains in the presence of heat and acidic contaminants. However, it is not just a chemical reaction, but an autocatalytic process where the degradation itself creates more water, further accelerating the damage. In addition, the presence of organic acids accelerates oxidation reactions in the transformer oil, thereby contributing to the progressive deterioration of the oil paper insulation system. Under the combined effect of thermal, oxidative, and hydrolytic degradation often leads to premature dielectric failure, resulting in costly and unplanned outages. Owing to its polar nature and high solubility in water, formic acid can be effectively removed from transformer oil using water extraction techniques. Low molecular weight acids can have underneath effect on paper. Number one, corrosion and degradation. These acids can corrode metallic components and accelerate the degradation of paper itself, causing to weaken the overall structural integrity of its insulation characteristics. Number two, lower pH is associated with a lower degree of polymerization. The insulating paper, usually kraft paper, performs optimally within a pH range 6.5 to 8. The pH value is critically important in a transformer insulation system because it serves as a primary indicator of chemical stability. A low pH, that is high acidity environment, promotes further and catalyzed hydrolysis that accelerates the degradation of cellulose polymer chains, causing the paper to become brittle and potentially leading to transformer failure. Number 3, hygroscopic nature. Low molecular weight acids are polar and hygroscopic, meaning they tend to absorb water molecules from their surroundings. These acids can act as carriers that transport moisture into the solid cellulose paper insulation, resulting in an increase in the moisture content of the paper. The combined presence of moisture and acids further accelerates chemical reactions that degrade cellulose, thereby reducing the overall effectiveness and reliability of the insulation system. Electrical properties. Presence of acids, electrical properties, presence of acids can adversely affect the dielectric properties of the insulation material. Acidic conditions may promote to initiate partial discharges or corona activity within the transformer, which progressively deteriorate the insulation and increase the likelihood of electrical faults and insulation system failure. Effect of acetic acid content dissolved in the transformer oil. The molecular weight, molar mass of acetic acid is 60.052 gram per mole, which is higher than that of formic acid, whose value is 46.025 gram per mole. Acetic acid, an organic acid produced in transformer oil, is also be a byproduct mainly from the decomposition of cellulose-based paper insulation and oxidation of the mineral transformer oil. The presence of acetic acid would greatly reduce the quality of insulation performance of a transformer, which thereby seriously affect the healthy operation of the transformer. It has already been exhibited that the low molecular weight acids, typically formic acid, levulinic acids, and acetic acid, are highly hydrophilic. As of the characteristics, approximately 90% of these acids tend to be absorbed by the oil-impregnated paper insulation, which leads to faster hydrolytic degradation of cellulose. Formic acid is stronger than acetic acid, and because of their structural differences, formic acid is more aggressive in degrading of cellulose insulation compared to acetic acid. In contrast, acetic acid mainly contributes to the overall acidity of the oil, which promotes sludge formation and deteriorates the dielectric properties of the insulating oil. Acetic acid thus acts as an acidic contaminant in transformer oil, and its accumulation results in a proportional increase in the total acid number, that is TAN value, or neutralization number, which indicates the level of oil degradation. Acetic acid is hydrophilic in nature, meaning it has a strong tendency to absorb and retain as moisture, retain in moisture. Retain moisture. This results in an increase in water content within the oil paper insulation system, which subsequently reduces the electrical resistance and dielectric strength of the insulation. Acetic acid can induce corrosion of metallic components, especially copper windings and transformer core, potentially leading to mechanical deterioration and reduced operational reliability. Acetic acid enhances the electrochemical corrosion of copper windings by facilitating cathodic reactions at the metal surface, which increases the dissolution of copper ions and subsequently results in the formation of copper sludge. Acetic acid promotes to localized heating corrosion of carbon steel components by acting as a buffering agent that supplies hydrogen ions, thereby destabilizing and destroying the protective oxide film on the metal surface, that is core part, that is on the core part. In addition, acetic acid can dissolve metals through the formation of soluble metal acetates, which may further catalyze the oxidation and degradation of the insulating oil. Difference in characteristics of acetic acid and formic acid as produced in mineral transformer oil. Characteristics: formic acid, then acetic acid. Molecular weight: low molecular weight, carboxylic acid of molar mass 46.025 gram per mole. Low molecular weight carboxylic acids of molar mass 60.052 gram per mole. Acid strength and stability: relatively strong, pKa value 3.75 at 25 degrees centigrade, and more stable in solution as the acid does not have an electron donating alkyl group. Comparatively, acetic acid is comparatively weaker, whose pKa value is 4.76 at 25 degrees centigrade, and less stable due to presence of electron donating alkyl group, that is CH3. Degradation of cellulose: more aggressive and dominant agent in the early stage. Low and long-term impact: low concentration, that is 3 milligram per meter cube, may not cause immediate or significant degradation. Higher concentration, that is from 20 to 200 milligram per meter cube, can lead to noticeable degradation after prolonged exposure. Solubility: about 90% typically absorbed by the insulating paper rather than remaining in the oil. About 90% typically absorbed by the insulating paper rather than remaining in the oil. Characteristics: pH of the system. Formic acid, in case of formic acid, increase in acidity lowers the pH of the system, which promotes corrosion of metallic components and reduces the dielectric strength of the insulation. Acetic acid, increase in acidity lowers the pH of the system, which promotes corrosion of metallic components and reduce the dielectric strength of the insulation. Reducing ability. The formic acid contains a unique structure possessing both a carboxyl group and an aldehyde group, that is CHO. Hence, like other aldehydes, formic acid can easily be oxidized to carbon dioxide and water. Therefore, it acts as a strong reducing agent. The acetic acid serves primarily to increase the acidity and catalyze the hydrolysis or aging process of the oil paper insulation rather than acting as a reducing agent in the oil's chemical environment. Reactivity. Presence of aldehyde group CHO that allows to have more reactive and be easily oxidized compared to other carboxylic acids. Less reactive as the acid lacks this aldehyde-like character. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.